In this lecture, we discuss why and where we use digital interpolation. While interpolation does not add any information to the signal, it does help us convert from the analog to digital domain, and back from the digital to analog domain. If we are dealing with a primarily digital system, such as an MP3 player, oftentimes the signal processing unit will be very sophisticated and powerful. So, we will want to make the analog circuitry as simple as possible to save power. In this case, upsampling and interpolating the output y of n can allow us to create a simpler analog filter that smooths out our zero-order hold. As a reminder, when we pass our digital filter output through a zero-order hold component, we multiply y sub d by a sinc function. After y sub n is passed through the zero-order hold, we need to filter y sub n with a low-pass filter that emphasizes the higher frequencies. In order for this D2A converter to work properly, the transition band of the filter must be very narrow. As the transition band becomes narrower, the analog filter will become more complicated and require more power. If we interpolate y sub n first, we can create a y sub d with much more space between the highest frequency of the k equals 0 replicate and the lowest frequency of the k equals -1 replicate. When we pass the interpolated signal through the zero-order hold component, the sinc function does not warp the k equals 0 replicate nearly as much as before. Therefore, the low-pass filter does not need to emphasize the higher frequencies as much, so the passband of the filter can be more or less flat. This again simplifies the analog circuit. In addition, since y sub d is narrower, the low-pass filter's transition band can be significantly wider. Since the transition band is wider, we ultimately create a cheap, low-power analog filter. The process of increasing the sampling frequency above the Nyquist frequency is called oversampling. I have just shown how oversampling is useful when constructing D to A converters, and I will now show how oversampling is useful when creating A to D converters. Let's suppose that we want our signal to be band limited to b radians per second, and then analyze the signal at the Nyquist frequency associated with the signal with such a band limit. However, the signal that we want to sample is not strictly band limited to b. To sample this signal and avoid aliasing, we can either low-pass filter the signal with an analog filter, or we can use an oversampling A to D converter to eliminate aliasing. To create an oversampling A to D converter, we need to sample the signal at D times the sampling frequency that we would normally use to sample the signal. After we sample the signal, we would low-pass filter the input and then downsample the input. Downsampling is a process where we sample the sampled signal and we keep only every dth sample. If we oversample the input signal, the dt-ft over the oversampled signal should hopefully diminish to 0 well before pi. To eliminate aliasing before we make the system have the sampling frequency we really want, we must apply a low-pass filter with amplitude 1 and cutoff frequency pi over d. After we apply the low-pass filter, the signal should abruptly reduce to 0 at the cutoff frequency. Therefore, when we downsample, we can stretch w sub d so that the abrupt drop-off will now be at -pi and pi, and the function will look smooth because downsampling will produce replicates on either side. Notice also that downsampling reduces the magnitude of the DTFT by a factor of D. If you are working with a system that already has a powerful digital signal processing unit, you should seriously consider using oversampling to reduce the complexity of your analog circuits. Digital interpolation allows us to make simpler D to A converters, and oversampling A to D converters help us avoid aliasing, yet still have a low effective sampling frequency for the digital system.